This is a photograph of a magnetic resonance imaging system from about 1996. Here sticking out of it, this is a optical diffusion imager. I was a subject in a test with this thing, so here you see me back then, and the depressing thing, of course, is how very young I looked in those days. Here, this Iron Maiden that's being screwed onto my head, that's the photon diffusion wave instrumentation. And then I went into the MRI and it created a tomographic image. So this is a tomographic image of my brain. Now, what's tomographic means that we can look at slices. So this is a cross-sectional slice. It's a volume image. And as we've seen, creation of multidimensional images is the core problem of computational imaging. Thus far in this series of lectures, we've looked at projection tomography, where we looked at X-ray propagation, and we used this Beer-Lambert law to describe the attenuation of a ray as it propagates through a material, and that creates this forward model. So the irradiance that we measure has been attenuated by moving through the media by this exponential factor. Now, we had to make this into a linear model that we could work with, so we assume that the attenuation is small so that this exponent becomes 1 minus this integral, and we assume that the measurement we make had this form. So we measure linear projections, and that was our model for X-ray projection imaging. Then in chapter 5, we looked at diffraction tomography. So we have a wave that's propagating through a material. We illuminate with a wave, and then we scatter based on the susceptibility of the material with the Green's function. So every point regenerates the wave, and we derive this Born series to describe the scattered wave. And we made the Born approximation to just take the first term in the series. So here we've substituted the original illumination wave in. This is a higher order Born term. We only keep the lowest order term, and this gives us a model for the scattered wave as a function of the illumination and the object density. So a forward model for tomographic imaging consists of creating a relationship between the measured field and the object density. So that's relatively complicated in diffraction tomography, relatively straightforward in ray projection tomography. Now we're talking about coherence fields, and so we need to develop a tomographic model for imaging with the coherence radiation, and that's the subject of today's episode. Computational imaging. Episode 44, Coherence Tomography. Suppose you had a point source radiating in space. So here we have our point here, and this is the real part of the wave amplitude. We see these sinusoidal modulation as the wave propagates away from the point source. Now, if we had a sensor, of course, we would measure the irradiance of the field, not the field amplitude. So no matter what we measured, we'd measure a constant. This would be what the magnitude of the wave looks like at any point in space. The purpose of optics is to code the irradiance so that when we make that measurement, we can reconstruct the source. Last time we talked about a rotational shear interferometer, for example, which takes the field created by the point source and folds it through the origin and interferes it with itself. This is what this looks like. So we have a point source here and a point source here. We've taken the original point source, flipped it through the origin, and interfered it with itself. And you see these interference fringes. And these are periodic fringes. If I take a slice at any point here, that would be a cosinusoidal modulation. Now, the interesting thing is if you look along this axis, what you see is that the period doesn't depend on where I make that slice. And what that means is that once I've chosen the relative angle of these 2 point sources, I get the same pattern. I get the same cosine independent of range to the objects. So again, as we talked about last time, this kind of measurement can be made with a rotational shear interferometer that flips the incident field along each axis so that I have the point flipped to the origin and interfere with itself to create this cosinusoidal pattern. And here's an example of what experimental data looks like, in this case for 2 point sources. So you see this beat and the 2 cosines created from 2 different point sources. Mathematically, we can represent what's going on here with the Van Sittert-Zernike theorem. As we saw a couple of episodes ago, if I have a spatially incoherent source, then the cross-spectral density that we measure at a remote plane with cross-plane coefficients x1 and x2, y1 and y2 from the original volume of the source, x, y, and z, we would use the coherent impulse response for propagating from the input positions to the output positions in each of the 2 dimensions to create the output cross-spectral density. In the case that impulse response is the Fresnel kernel, this simplifies to this relationship. So this is now a three-dimensional relationship for a source distributed over x, y, and z, and we have a simple Fourier transform relationship where delta x is x1 minus x2, delta y is y1 minus y2, and this parameter q has a strange form of x times x bar times delta x plus y bar times delta y. So it's actually a squared parameter, but can be represented formally in this form. And now we have a simple integral over 1 over z as our z parameter. All right, so that's the Van Sittert-Zernike theorem saying that our measured cross-spectral density in these coordinates is the Fourier transform of the object, and that corresponds to the idea that if the image is a delta function, for example, then we would just get the exponential form for the cross-spectral density. Now, with an RSI, we measure the cross-spectral density plus the cross-spectral density's conjugate, or actually the mutual intensity plus the conjugate, and that turns this exponential form into the cosine that we saw in the last slide. Now, here's what's cool. If you take this Fourier transform relationship, we can Fourier transform and get that the Fourier transform of the cross-spectral density is just the integral of the object along z. We've taken the Fourier transform and the coefficients delta x, delta y. The z part still remains, and so it turns out that the Fourier transform of the cross-spectral density with respect to delta x, delta y, because the cosine pattern that we get doesn't depend on z. All different z's along this particular angular direction, theta x, theta y, produce the same cosinusoidal pattern on the RSI. What we see is the integral along those particular angular directions through the object. In other words, we're seeing the linear projection, the X-ray projection through the object by taking the Fourier transform of the cross-spectral density. So amazingly, the form of tomographic imaging with coherence fields is actually a lot simpler than the form of diffraction tomography. So now we have a model for how we can image tomographically with the cross-spectral density using the same model that we used for projection tomography way back in episode 22. This is done in this paper. Here we have the only paper probably that ever published an image of a toy dinosaur in science. And so we had an RSI imager, you have an object, you rotate the object, so then exactly as we saw back in episode 22, by rotating the object, we obtain a set of projections that we could use, filtered back projection now in a very direct way to create a tomographic image of the object. This particular object was not transparent, so the surface creates these artifacts because we're assuming that we're imaging along the volume, but we're actually imaging a surface object. And we can create the same kind of 2D slices you saw of my head from the MRI, but in this case, of course, the slices have artifacts because the object is not actually transparent. But this approach can be used to create tomographic images. We're going to talk a lot throughout the rest of our episodes about how we effectively measure the mutual coherence with focal systems and with interferometry, and this is a active and interesting area for continuing thought about how we can create tomographic imaging systems. But next time, we're going to step way back in time to episode 10, where we talked about resolution limits and the Raleigh criteria. In episode 10, we looked at, as we have 2-point sources, here's 2-point sources that get closer and closer together, they start to look like 1-point source. This is a measurement you would get with a focal system. This is measurement you would get with an RSI. We're going to talk about how these measurements can be used to evaluate the relative separation of the point sources in our next episode.